right, so now we'll get into calculating energy changes from a chemical reaction. And often I maybe just want to know overall, will this chemical reaction be endothermic or exothermic? Overall, where are we at here? Energy absorbed by a system, which would mean that the reaction is endothermic, will cool the surroundings as we suck energy out of the surroundings into the system, into my reaction. Or is energy overall released? If there's a release in energy, the reaction is exothermic. Energy is released by the system, by the reaction, to warm the surroundings. We can calculate the amount of heat exchanged in a chemical reaction, which is important sometimes. But yeah, often qualitatively, I might just want to know, is it endothermic or exothermic? To do that, we need some data called bond enthalpy, or sometimes we just call it bond energies. It is defined as the amount of energy needed to break 1 mole of bonds. Now, this is important. Breaking bonds will absorb energy. Hello. Energy is absorbed when bonds are broken. Super important concept to understand. Because again, think about these bonds. Bonding is a good thing. When atoms are bonded, whether they're sharing electrons or transferring electrons, but that's how they have their full outer shells, and that's what makes them stable. So if I'm going to come in and break a bond, I need to add energy. That could be in the form of heat or electricity. I need some kind of energy source to break apart the bonds. Think about magnets that are very attracted to each other. If I want to separate those magnets, I need to add a little elbow grease. I need to add a little energy. But on the flip side, energy is released when bonds are formed. Energy is released when new bonds are formed. When a new bond is formed, then the atoms should be more stable. When they form their new bonds, they should drop to a lower, more stable energy level, as now the atoms do get their full octets again. So breaking bonds, think about magnets. I have to add energy, separate magnets. But if I have two magnets that are attracted to each other, often they kind of like snap together. And as they snap together, think of it as like releasing energy when I make new bonds. Interesting. Okay, so we've got this chart here. We've got this table of average bond enthalpies or bond energies in units of kilojoules per mole. Joules or kilojoules is a unit that we're going to use to quantify heat. It could be either joules or kilojoules. It's like a metric unit for heat. Kilojoules per mole of bonds. Okay, so we've got like a hydrogen-hydrogen single bond. We've got a hydrogen-fluorine single bond, a hydrogen-oxygen single bond. Then they give me like some double bonds and triple bonds. One thing that's kind of interesting to note is that as you go from a single bond to a double bond to a triple bond, and there's more electrons being shared, it does take more energy to break the bond. For example, here I can see there's a nitrogen-nitrogen double bond with a bond enthalpy of 418 kilojoules per mole. But then I also see the nitrogen-nitrogen triple bond at 945 kilojoules per mole. So it definitely takes more energy to break a triple bond. Now, obviously, this little table doesn't have every bond out there. And I can show you a bigger table that has all kinds of different bonds. But if they ask me to predict the bond energy of a nitrogen-nitrogen single bond, well, if it's a single bond, there's only 2 electrons shared, so I would expect the bond enthalpy to be a little less than the 418. It should be easiest to break a single bond versus a double or a triple bond. Okay, so we almost have to kind of think about our Lewis dot structures from like back at Christmas time. That let's say I have the hydrogen molecule. So here's a hydrogen molecule, single bond. So if I want to break that bond, I need to add energy from the surroundings. Now that may be that I have a Bunsen burner or like an electric current or something like that. But there needs to be an outside energy source available. So if I add 432 kilojoules, I can break a mole of those hydrogen bonds. Hydrogen single bonds. And now we get to the top here where we've got those two atoms that are separated. And up at this high energy level, the atoms are not stable. Now those atoms do not have their full octet, or in this case, a duet with just hydrogen filling the 1s orbital. But those atoms are not stable when they don't have that full outer shell. So I have to add energy to break the bonds. But on the flip side, if I release energy, I'll form the bond. So you add 432 kilojoules to break the bonds, but then I'll release 432 kilojoules when the bonds are formed. And so I think this is interesting that they're showing here that energy is absorbed from the surroundings to break the bonds, but then energy is released to the surroundings when the new bond forms. This is important. Right in there. Breaking bonds and forming bonds. They're just the opposite process. They involve the same quantity of energy being exchanged. But maybe we should just make a note that whenever you see a positive delta H, it means the change is endothermic. Energy is being added. Now, bond energies are defined as the energy that needs to be added to break the bond. It's energy needed to break the bond. But it's also the same amount of energy released when the bond forms. It's the same quantity of heat. The difference is just the direction of the energy flow. We have to add the heat to break the bond, but then we'll release the heat when the bond is formed. So same quantity. I add 432 kilojoules to break the bond. I'll release 432 kilojoules when the bond forms. So when you see like the positive delta H endothermic, I'm adding the energy to break the bonds. Negative delta H, I'm releasing the energy when the bonds form. Now again, the table only lists these values in positive terms because it's defined as energy needed to break the bond. But if I just put a negative in front, it's the amount of energy released when the bond forms. So for example, I've got an oxygen-oxygen double bond. I have to add 498 kilojoules to break the bond. I'll release 498 kilojoules when the oxygen-oxygen double bond forms. So these are kilojoules per mole of bonds, defined in the positive endothermic direction. But I can also use them in the exothermic direction. Question 6 says, how much energy would it take to break all the bonds in 2 moles of oxygen gas? Okay, so no big deal. I gotta go to my table and find the oxygen bond, which we were just mentioning. Now, sometimes it may help to draw the dot structure, but if I've got that oxygen, oh my goodness, this is like from light years ago. 1, 2, 3, 4, 5, 6. Oxygen's got 6 valence electrons. And we'll link them up in a double bond to give everybody an octet. Now here there's only one choice. My only option is the oxygen-oxygen double bond. But eventually we might have to kind of think about the dot structures. If they would have given me a single bond and a double bond, I got to think, okay, well, what kind of bond is this? So again, it tells me 498 kilojoules per mole. Well, that's the amount of energy needed to break 1 mole of bonds. If I want to break 2 moles of bonds, we just multiply. Kilojoules per mole, I multiply by 2 if I got 2 moles of bonds. Oh, that kind of makes sense, right? 298 times 2 should be about 996 kilojoules. I I could break a half a mole of bonds, and I would just take 1/2 times that 498. Now, all those bond energies have to be given to you. Those are constants that would be given to you on a table, and then we'll use those values to determine how much energy is absorbed or released from different chemical reactions.